Okay, so in this part of the course, we're going to start chapter 5, which is on logic, and logic provides the foundation for mathematics, especially if we're going to start talking about proofwriting and things. We need to understand logic. We need to understand what these mathematical statements mean and what they require from a proof. And in order to start that out, we need to talk about basically like what are the things that we are going to work with when we talk about logic. And so that's going to boil down to a definition of what a statement is. So let me give you the definition. So a statement, which is the kind of things that we tend to make in mathematics, but what do I mean by a statement? Is a sentence or mathematical expression that is either true or false. Okay, so there's lots of different statements that we can make in mathematics. Some examples are that square root of 2 is a real number. That's a statement. We could say that pi is a real number. That's a statement. We could say that 3 plus 7 equals 10. We could say that sine of x is a continuous function. We could say that absolute value of x is a differentiable function. We could say that square root of 3 is in the integers. We could say that 7 plus 10 equals 25. So under our definition, all of these things are statements because they're all sentences or mathematical expressions which can be labeled true or false. So the first several of them are true, and the last few are false. Forgive me for my ugly brackets. The iPad doesn't help with my handwriting. So what about some non-examples of sentences, right? So these are all sentences for the reasons that I just said, and some non-examples would be the following. Just 8 plus 15, or something like x squared plus x plus 3, or the natural numbers, or are trig functions continuous. Right, these are not statements in the sense that we just defined, because we cannot assign a truth value, right? So the issue is that we cannot assign a truth value to these non-examples. Okay, so again, we need to be a little bit careful about what statements are, only because we're about to learn some logic which will involve some sort of calculations that we can do with statements, and we need to understand like what it is that we want to be able to work with when we're talking about logic. We want to be able to work with these sentences or mathematical expressions that can be labeled as true or false. That's the important part. Okay, so related to this is something called an open sentence. So it's not going to be a statement technically, but it's going to be related. So a related notion is that of an open sentence And I'm just going to define this by example. So like f is continuous, which would be a statement once we know what function f represents. This is actually very common in mathematics, where we are usually giving a lot of open sentences where they involve some variable that we don't know yet, but once you know what the variable is, you can decide the truth value of the sentence. So that's why this is very important. So like other examples are x plus 13 equals 25. Well, I don't know the truth of that yet, but I could, if you tell me what x is, I could tell you whether it's true or not. Or something like 3 divides n, or m is even, and something like g is differentiable. In all these examples, the reason why it's not a statement is just because there's some free variable that I need to know what it is first before I can decide whether it's true or false, right? Okay, so good. That's going to be, so statements and open sentences are going to be the kinds of things that we can play around with in logic. Okay, so now let's start to introduce some notation. So if P and Q are statements or open sentences, then one, if I write P and then this symbol Q, that means we say P and Q in that case, and then two, we can say P, this symbol Q, which means P or Q. And then the last one is we could say tilde P, which means not P. Okay, so what's going on here is that P and Q are going to be the variables now for logic, but these variables in logic are going to stand for statements or open sentences. And we need ways of combining these statements or open sentences in the form of variables together. So far I'm introducing and, or, and not. Okay, so let's play a little bit around with this new notation combined with sentences, statements and open sentences. So some examples. So first of all, let's let P be the statement that the number 3 is odd. Let's let Q be the statement that the number 4 is even. Let's let R be the statement that the number 5 is even. And we'll let S be the statement the number 6 is odd. All right, so of course we know some of these are true and some of them are false, right? So this first one is true. This one is true. One is false. This one is false. Fine. And we just want to play around with the ands and ors and things in this very basic situation. So first of all, we could do P and Q, which is the statement that 3 is odd and 4 is even. Or we could do P and R, which is the statement that 3 is odd and 5 is even. Okay, so the first one is true because it's an and they're both true. And the second one is false because even though 3 is odd, 5 is not even. And so if you want both of them to be true, then um, it's not true in that case that they're both true. Good. Now, 2, we can do P or R. That says that 3 is odd or 5 is even. And we could do, just to play around, R or S. So that says that 5 is even or 6 is odd. So now the first one is true because it's an or and you only need one of them to be true. And the second one is false because they're both false. And so the or is not true. Now I'm going to define ands and ors like very carefully in a second, but the reason why I'm doing this, playing around a little bit, is because you already have an understanding of how ands and ors work in regular old language, and so you don't necessarily need the definition uh, quite yet to make sense of all these statements, right? So then the way not works, not P means that 3 is not odd. But because odd is how it's defined, not odd means even, right? And then not S is the statement 6 is not odd. And of course, 3 is odd, so the statement 3 is not odd is false, but 6 is not odd, so the statement 6 is not odd is true. Great. And then for the last part of this example, let me just play around with combining these a little bit. So we could do P and not Q. So then we're saying 3 is odd and 4 is not even. Or we could say S or not S, which is saying that 6 is odd or 6 is not odd. Okay, so in this case, the first one, 3 is odd and 4 is not even. That is false because 4 is even. So, and you need both of them to be true. The second one is true no matter what number we plug in because it's saying the number is odd or the number is not odd. So that's true for any number that we can plug in, a natural number. And so it's certainly true for 6. Okay, great. Let's continue to introduce the logical connectives. So far we've done ands, ors, and nots. So what else could we combine statements and open sentences? How else can we do that? Well, there's two more important ones. So notation, again, let P and Q be statements or open sentences. And then one, we say that P, this symbol Q, means P implies Q. And then we say that P, this symbol Q. I can't say what the symbol is the first time, but afterwards we'll always, when I'll say the symbol out loud as P implies Q in number 1. And the second one is P if and only if Q. But we'll see later that if and only if is a double implication. We just, in language, oftentimes in mathematics, we use this shorthand where we double up the F on the if to mean if and only if. So I'll just remind you of that. I think I've said that before. So these are the other important logical connectives that we'll need. And most statements in mathematics involve some kind of implication or equivalence via an if and only if. So that's really important. And, when we're doing logic, one of the reasons why we're going to be so careful about, ands, ors, nots, implications, if and only ifs, and trying to communicate exactly what they mean is because in everyday language, we're a little bit sloppy about these things. And so if you just try to use everyday language, which we will use in mathematics, but if we only use everyday language, then we're going to make mistakes in communicating what we really mean. So the goal in mathematics is to have a language which is unambiguous. And we don't always completely, make it to that ideal, but we at least ground it, everything we do in unambiguous language via logic. So that's part of our goal here, is to introduce an unambiguous language so that we can um, be rigorous in our proofs. Okay, now I want to make a definition of something involving implication. So first of all, we're going to call something called the converse. So the converse of P implies Q is Q implies P. Okay, so very often a theorem in mathematics will be written not with P's and Q's, but will be of the logical form of P implies Q. And then oftentimes a question that someone will ask, you could ask as a student, or other mathematicians will ask each other in talks and things, is whether or not the converse is true. And because it's not, we'll see later on that the converse does not logically follow from an implication, but sometimes we prove the implication P implies Q, and it turns out that the converse is also true. Oftentimes the converse is not true, but it's very insightful to see why the converse is not true. So that's why it's a good question. And anyway, I'm just bringing that up now, but you'll need to see examples of what I mean. And so I will show you examples of that at other points in the course when we are actually looking at proofs. But I want to just bring it up now. And the converse is a really important thing in mathematics, so we want to understand it. Let's just do a simple example. So we could have n is even be the open sentence for P, and we could have Q be n is an integer. Okay, so then we can look at P implies Q, and we can look at its converse, Q implies P. So we can write both things down, right? But not both of them will be true necessarily. So P implies Q is true, right? Because n being even implies that it's an integer, so that's true. But Q is not, Q does not imply P, because n being an integer does not imply that it's even, so that's false. Now this is a little bit tricky because this is involving open sentences. And so it really kind of depends on what n is, right? It's possible that if n was 7, then in that case, 7 is an integer, but 7 is also even, right? But in general, for open sentences, this is an important thing that we do in mathematics. The fact that n is even implies that it's an integer, but the fact that n is an integer does not imply that it is an even integer. Good. Okay, so we'll see more of converses throughout the rest of the course. This is just me introducing it formally and what it means in terms of implication and logic. And in the next videos, we'll have to start to play with truth tables for these different logical connectives, which will define exactly what these logical connectives stand for.